open. I hope I still have this open. Let's see. Gonna move this. Dun, 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 dun. What I wanted to do, I hope yesterday went. Go ahead and put it on my chair. Thank you. I appreciate the volunteering. Um, nope, nope. Did I get rid of it? I did. I got it. Okay, good. So hopefully yesterday's homework went all right. 15, just a circle. R equals theta equals is just a line. And the best way I can explain it is when you have negative radii, it just flips over to the other side. That's why we have this part of the line as well. There's nowhere to throw in R, but you can throw in any R, and that's what ends up happening. And they were actually asking you to do changing them to rectangular, didn't they? Didn't they ask you to change them to rectangular? All right, so we have this key, another line, another line. What I really want you to understand is this. Look at the circle. So 2 cosine theta. Notice the cosine graphs are either, I wish there was better than this, right, or it could have been on the left if I had negative 2 cosine theta. That would be true. So this would just be over here on the left side. And then notice how far that is. That's 2 away from the pole. 2, 2. Okay? And then look at the sign. Unfortunately, I don't have a positive sign either. I wish I could make that, conjecture here with you. But this is 4 from the pole. 4, 4. And it's down instead of up. So if that was positive 4 sine theta, it would just be a circle up here, right? Instead of down there. Got it? So sines up, down, cosines right or left, depending if it's positive or negative. Unfortunately, I don't think you have all those keys. Why does this not work? Okay, so it's another positive cosine, so it is 4 to the right. I guarantee you if it was negative, it would be over here on the left side. Then another negative sign, so it's down. Wish we had a positive sign so you could see it's up. Because that is going to stick with us today. We are going to build on that. That is today's notes. Ooh, and this is on our, we're going to use this. It's on our calendar. I remember I used this last year with my A-Bers. Just a little Desmos making conjectures about what the graphs look like on a polar coordinate plane. Okay, input, say it. I got no time. Oh, no. I sabotaged myself. Okay, 0, comma, 0. All right, and then after a while, I'm going to get a little bit lazy because this gets a little tedious. 0, 0. That's that point. All right, and then how do we get these input outputs? Cosine of pi over 6 is root 3 over 2. Root 3 over 2 times 4 is 2 root 3. Then we get a decimal for that. Careful, I made this mistake last hour. This is the over 12s. So I really wish they weren't there. They are confusing me when I'm doing this. And then that's just at a half there, so it's really small. Okay? And then pi over 4 is 1.2 if you just accept my math there. And then 4, okay, pi over 3 is half of 4 is 2. So at pi over 3, did I go off? I did go off. Man, it's so hard. Hold on. No, I did not. This is pi over 12. See, this is tough. Tough. Really tough. Okay, to stick on these with that pi over 12 listed in there. Okay, so this is pi over 6. And what was that one? 0.5, right? I think that one I was off. Then this one was 1.2. And then this one was 2, correct? Okay, now I got it. I had to zoom in because these lines, the over 12s, are messing with me. You know what? I quit. I'm going right to, well, I guess not really. Pi over 2 is not a quit. That's at 4. 1, 2, 3, 4. And then this is what we got in a nice little progression. We got this little curve there, and you connect them. Got it? Okay, this is kind of a graphing 101. There is no way in heck you're graphing like this. You make a conjecture, and we're going to get like 4 points, and that's it. But I'm just trying to make sense out of the situation. So fat or mac, I may do one more. 2 pi over 3 comma 6. Here's the over 12. This is, and then is that 6? 1, 2, 3, 4, 5, 6. And then I'm skipping right to pi. Cosine of pi is -1, but that's times -4. That's how I get 8. This is 6, 7, 8. So then it continues out and then bubbles out to this high point right there. That is as far as it can get away from the origin. What's 4 plus 4? 8. So that's why that is 8 out, and that's the max it could possibly be. Then when you start going to the other side here, 4 pi over 3 is 6. I'm going to skip to that, and then that's 6. That's symmetric with this point, and then all the other points would do something like that. Doink. And then I'm going to cheat and go to 3 pi over 2, which is 4. 1, 2, 3, 4. And then that continues the, symmetry right there. I definitely have symmetry here, so I get what's happening here. And then I get all the way to 11 pi over 6, which is right here. Not that one, half. And then 2 pi is the same at, oops, 0. Hey, what does that look like? Ba-boom, ba-boom, ba-boom. What does that look like? Okay, why do you think it's called this? Because it looks like a what? Oh my gosh. Oh, a heart. What are you guys doing? Okay, and then, did you say that? Okay, so here's cardioids and limacons. Y equals A plus or minus B, and then I'm going to put sine or cosine. Watch the sine. Oh, I'm going to say it right now. Sine or cosine of theta. Okay? For a cardioid, you're going to find out that A equals B for me to have a cardioid. See? 4 equals 4. And then look at our thing here. This is a minus cosine. Where's the main part of the graph at? Left, right, up, or down? To the left, the negative x-axis. Huh? That's what I was trying to show you with your yesterday's homework. A cosine circle was either on the right side or left. You only had positive ones. And then you only had negative signs, which was on the bottom. All right? And then that's not a coincidence that this is 8 out right there. What's 4 plus 4, everybody? 8. So these are our conjectures for this. All right? And that's what we need to make a sense out of right away and lock and do memorization. Okay, they did expect you, I think it says graphing calculator because we don't have time for this, but I'm going to go ahead and go to what is on the calendar. I'm trying to find myself. It's right here. I already have it opened. So hit that and it opens, right? This is for later from when we were dealing with the other period. Okay, what do we have here in our next one? 1 minus sign. Okay, if you're with me, you should expect 1 minus sign, 1 minus 1 sign, up, down, right, or left. Where's the most part of the graph at? Up, down, right, or left? Down, negative y-axis. All right, and then how far down does it go? What's 1 plus 1? 2. But it was 1 minus, and then there you go. And then there's that cardioid, that point that happens here. Watch how this works, though. You get to watch this in action. Pull this toggle, and then you get to see the graph. Input, say it. So as you input through the first quadrant, second quadrant, third quadrant of values, and then fourth quadrant of values. That's how it creates that picture if you were going to do an input-output. All right, next one. Okay, got to get on this right away. Let's go to the third one. Where do you expect that? Up, down, right, or left, the majority of the graph? To the right. And then what's 1 plus 1? 2. So our biggest point. So this was plus. And then I'll go beyond this. I'll go look at a positive sign. It's up. Positive cosine is to the right. And then this is a distance of 2 from the origin. By the way, what's 2 minus 2? What's 2 minus 2? 0. That's why this is on the origin. You're going to see this when this changes, when I start changing the A and B values. Okay? All right. But let's get a better picture. Let's say like 3 and 3. Let's do 3 and 3. What's 3 plus 3, by the way, everyone? 6. Guess what? This is 6 out all the way over here. 6 out. Okay? So I'll tell you what I do on the graphing. I only do 4 points. I do 0, pi over 2, 3 pi over 2, pi, and then I know what my picture looks like. Okay, I know what's supposed to happen. One more thing I want to do. We do this with the A-Bers, and I'm surprised we don't do this with you guys. I like comparing the rectangular graph because that's what AP did. And I thought it was it actually made my life easy on analyzing these. And I think it made it really smooth for the A-Bers last year. Like I was terrified that this was the last subject before the AP test for the A-Bers. And actually the way AP approached it made it super simple. All right, so we know this goes 4 up, so that's 4. This is a cosine kid, but it's upside down, and it goes 4 up and 4 down, and the graph starts here, and then it goes up to the high point, back to this, and then back to the low point. And then this is what the graph looks like. What I want you to know is these points all coincide. That point is that point. The pi over 2 point is this point. This point is this point. This point is this point. Wrong, 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 wrong. That was a stray. That was a stray. That's that point. And then when you get back to 2 pi, you're back to where you started. That's why the graph is complete. All right. And then what we tell our A-Bers is for a cardioid, these values right here are right on the x-axis. They'll go above or below. There's no above or below. All right. And then this really helped me on the next two, what occurs. So here's how I graph this by hand. These are equal. So I have a cardioid that's locked in. That's memorization. This one is just written weird. This is 5 minus 5 cosine. These are equal, so this is a cardioid. I could do 0, pi over 2 pi, 3 pi over 2 to prove it's right, left, up, or down. We should already know that. Go ahead and make pictures of these real quick. I'm going to freeze the screen. You do your own sketches. I'm going to freeze the screen. You guys in video land, YouTube land, will see me do this as we go. I plug in 0. Sine of 0 is what? What's sine of 0? Times 3 plus 3. What's sine of pi over 2? That. And then I get that as an output value. What's sine of pi? 0. 0 times 3 plus 3. Right? And then what's sine of 3 pi over 2? Oh, that's negative 1 times 3. It's this. And I know this is so this. Widen it out. This. And I know that this one is a cosine, so shoot over here. So this. Then when I go ahead and plug in 0, cosine of 0, cosine of 0 is 1. 5 minus 5 times 1. Cosine of pi over 2 is 0. 1, 2, 3, 4, 5. Cosine of negative pi is negative 1 times negative 5. Oh no, it's off the screen. What am I going to do? And then what's cosine of 3 pi over 2? 0. 5 is 1, 2, 3, 5. Okay, and then, all right, so I know it's supposed to be a cardioid, so it does something like this. Round it out. Round it out. And then that's quick extrapolations. Quick extrapolations. Then I'll go to my key here. Okay, so I did do, and we're limited on time here, so I don't want to spend too much time on this. Boom. How many people got those little drawings there? Okay, now this one was off the screen because what's 5 plus 5? 10. So I had to show 10 all the way to the left there. But I did plug it in. Cosine of pi is negative 1. So 5 minus 5 times negative 1 is 10. All right, that's why it's pi comma 10. All right, and then I did do the pi over 2 and the 3 pi over 2, which are 0. But that's 5 minus 0 in both cases, which is 5. And then I just know it's supposed to be a cardioid. This is what we're going to have to do to lock in. We are not doing this. There is no way in heck that you are going to be inputting, outputting all of these points to get a picture. They're just extrapolations. Then at this point, you got to make the extrapolation happen in your head. Okay? All right. And I just plugged some of these on our little generator there. I also had my calculator ready. I guess I didn't even use that though with the other hour. But I did put it in mode polar, and I could do it on that, but I'm just going to use my Desmos thing. All right. And it works pretty good. Okay, a limason. Okay, now there are two types of limasons. This is one where we have a dimple, or it's called convex. So what we're having here is a y equals a plus or minus b sine or cosine. I don't know why I'm writing it again, but really all I wanted to show is this is when a is larger than b. What happens? Well, I want to show you what happens with the regular graph in rectangular form, and then show you how that translates into our graph on a polar coordinate plane. This goes up 3, 1, 2, 3. That's our midline. This time we're graphing a sine, and it only goes 2 up and 2 down. So this one does not touch the x-axis. This one stays above the x-axis. And then this is 2 pi, pi over 2. And then we'll go to our Desmos cheater and show how this actually works. All right, and then how does this graph sign is middle, high, middle. What? Why did I put a 3 there? That's 3. This is 5. 3 plus 2 is 5. My bad, dogs. Okay, then we're actually going to graph these. What's 0? I should be getting 3. Well, that's true. Sine of 0 is 0. 0 times 2 is 0. 0 plus 3 is 3. So I'm going to use these points right here. 1, 2, 3. And then sine of pi over 2 is 5. 1, 2, 3, 4, 5. By the way, I got a positive sign. So I expect most of my graph to be above along the positive y-axis if I throw a rectangular coordinate plane there. Sine of pi is 3, 1, 2, 3, symmetry. But then what doesn't happen is sine of 3 pi over 2, I get 1. I don't get back to the origin. So I don't have what's considered a cardioid where I get back to the pole. I'll use that word as well. All right, and then sine of 2 pi gets really back to this. So what happens here and here? I'll plug in something simple like 7 pi over 6. What's sine of 7 pi over 6? Negative a half. Negative a half of 2 is negative 1. Negative 1 plus 3 is 2. So 1, 2. And then the same thing happens at 11 pi over 6. Same output. It's always hard with this one in there. 1, 2. So here's what happens. You start here. It does kind of widen out there. You want to make this kind of look circular. But then what it does is hits this and then bounces back out. So it kind of looks like a cardioid, but it doesn't make it back to the pole. So therefore it's called a limason. Can everyone say limason? I often say limacon, but then I look it up and I think they put a little thing above the C that says it's so, and then they put a little thing above the I where it makes it limason. Okay, so anyway, that's a limason. Hey, what's 3 minus 2, everybody? 1. Do you see that distance right there from the pole? That's a distance of 1. Hey, everybody, what's 3 plus 2? 5. Do you see how that's 5 up right there? So these differences are shown in the graph here. This is what you need to figure out. Okay? So the difference between 3 and 2 is 1. That's how far the dimple is away from the origin, all right, or the pole. And then 3 plus 2, 5, that's how far the longest point is and know that this is a positive sign, so it's 5 up. But you can input output and prove that that's what's going on there. You usually only do 4 points, and then I know what I'm dealing with, so I know what to graph after that. Okay, now this is a little bit weirder. This one, so we'll do, and actually both of these are, because these don't show a dimple, and I'm going to go to the grapher on that one. So what was that? 4 minus 2, right? So 4 minus 2. There we go. Is that a dimple? Yes or no? Not really. This is starting to be flattened out. So this is called a convex. What's the matter? Did I do something wrong? Oh, it's supposed to be sine, right? That's to the left. I should have known that. And this is supposed to be down. There you go. But anyway, this is a called a. Can you get ready to say this? Convex limacon. Say it. Okay, this is not a dimple anymore. As a fatter mac, as this gets, and notice what this is. This is double this. This is what I'm going to tell you about, like its relationships here. When it's not, when it's like when this is a 3, then I get the dimple. See that? It's only one big. Once it's double or more, then this becomes more circular, more convex, more pushed out. Do you see that? Now I made it 5. All right. So, but what's the difference between 5 and 2? What's the difference between 5 and 2? 3. What's the sum of 5 and 2? 7. So this bottom point is 7 away from the pole. This non-dimpled convex part is the difference of 5 and 2. 3 away. Huh? That. Okay. So these are the things that we kind of have to lock in. Now, I know that wasn't one of mine up there. I was just playing around with the numbers. Well, okay. I had 5 minus 2 cosine. I'll just change that to cosine. And then what can we expect? I accidentally hit that. We can expect this flips over to be on the left side. So cosine is right, left. If it's a negative cosine, more of it's on the left. The more circular part, the part that's farthest away from the pole, is on the left. And then it's 3 to the right over there. And actually, I should be playing with this. You get to play around with drawing this. This is the order. When I input 0, I get 3. And then as I input more and more, it's growing, growing, growing. And now I'm almost at pi, which is 3.14. When I plug in 3.14, I get 5 plus 2, which is 7, right there. 3.15, it came so close. 3.14, so close. Okay, so this helps you understand the input outputting if you look at this Desmos thing, right? It's kind of fun to toggle with this kind of thing. Good learning tool. Okay, so how would I graph this? I know this is a limacon. I know 4 plus 3 is 7, and I know this is a positive sign. Or, okay, let me just plug it in. Sine of 0 is 0. 0 plus 4 is 4. 1, 2, 3, 4. Okay, sine of pi over 2 is 1. 1 plus 3 is 7. You're a little bit off the thing. Sine of pi is 0. 0 times 3 plus 4 is 4. 1, 2, 3, 4. Sine of 3 pi over 2, there's the difference. Sine of 3 pi over 2 is negative 1 times 3. Negative 1, or 4 minus 3 is 1. Now, I could do one more to show that this is more dimpled. And what I like is the half value. So I'm going to do 7 pi over 6 again. 7 pi over 6 right here, and 11 pi over 6. Then we'll see that it comes out and then dimples in. Sine of 7 pi over 6 is negative a half. Negative a half of 3 is negative 1.5. Plus 4 is 2.5. So 1, 2.5. There it is, a little bit larger. And then same thing with this one. 1, 2.5. So how do I graph this? It's without having to do all of them. Boom, boom, boom. Little bit of a dimple, but not all the way back to the origin. Why is it a little bit dimpled? 4 is not double 3. 4 is not double 3. Watch this next one. 3 plus cosine. Cosine of 0 is 1. 1 plus 3 is 4. This is my whole point about this is a positive cosine, so the biggest part's on the right side. Okay, not a negative cosine. All right, cosine of pi over 2 is 0. 0 plus 3 is 3. Cosine of pi is -1. -1 plus 3 is 2. There's that convex part. It's pushed out a little bit. It's not dimpled anymore. It's pushed out. That's what. Hey, I don't want to be weird, but belly buttons. Sorry, I was thinking about this earlier. Don't some people have innies and some people have outies? this is an innie, and this is going to be an outie. Is that bad? I don't know. I don't know. You know, people are so sensitive these days. I can't even bring up anything. How dare you bring up belly buttons? All right. Anyway, okay. So one more thing. Let's do cosine's half value, which is 2 pi over 3. And cosine of 2 pi over 3 is -1/2. -1/2 plus 3 is 2.5. 2.5. So what I'm trying to show is it doesn't come out and then dimple back in. Like this is the farthest point out here. Well, actually, it's kind of not farther out there, but it doesn't really dimple in. And then this is 4 pi over 3. Cosine of 4 pi over 3 is -1/2 plus. Okay, so when I graph this out, you kind of want to elongate this and make it kind of circular, and then it just flattens out. As a matter of fact, I think I did this on the thing. Yeah, that was bad at the end. Sometimes it's kind of hard. That was really bad. This should be more circular like that. Okay, but anyway, I don't want to rewrite it. I'll get real obnoxious. Who, you, Mr. S? No way. Let's go crazy. You want to get nuts? Let's get nuts. Let's really show the, let's like make this like 9. Oh man. Look at that. What does that actually look like? It looks like a circle. It's because this is so pushed out so far that it doesn't really, show that dimple in there. All right. That's why that's so pushed out so far. But what's 9 minus 2? That's a good answer. Some people got their calculator out. All right. That's what the red dot's at. Okay, get ready for that. What's 9 plus 2? That's 11 right there. So it's 11 far out from on the left side. It's only 7 out on the right side. Are you okay over there? Next. Okay, a limacon with a loop. A loop-de-loop. Boy, I really jacked this up last hour. I was trying to go real fast with conjectures, and I really jacked up my graph. Did I not do this? I did do this, but I didn't finish the graph. This never hits the axis, right? Never hits the axis, right? Never dips below. I really like, this is where this really helped me, because I had hard times remembering when do I have a limacon with a dimple or convex, or when do I have a loop? And this is now, I got it locked in. I can think about the rectangular graph, and now I always know when I have a loop. And when I have a loop is when I have this. 1 up, there's your midline, and then it goes 3 up from here. 1, 2, 3. I'm just graphing this, but in a rectangular coordinate plane. Y equals 1 minus 3 cosine. Love this. And then down 3, 0, 1, -2. Now, it is a minus cosine, so it starts down. Let me get my x values. 2 pi, pi, pi over 2, 3 pi over 2. And then it hits the midline, and then goes above, and then hits the midline and goes below. Here's where we got a problem. Whenever we dip below the x-axis, this creates a very unique thing in a polar coordinate plane. So all of this creates a loop. It's because of the negative radius and how it graphs, how a negative radius graphs. So right off the bat, what's the cosine of 0? 1. What's 1 minus 3? -2. So here's how this graphs. 0, comma, not 2, -2. So I'm going to go ahead and erase that point. That's how you graph 0, comma, -2. Believe it or not, that's part of your loop. And I do have to keep going with these negative values to really show you this. So pi over 6, which is right here. What the heck? I don't think I hit the eraser. Pi over 6 is -1.6, but it's over here. -1.6 right there. Pi over 4 is -1.1, except that that's 1 minus 3 times root 2 over 2. All right, and then that becomes over here, which is -1. This is so hard to do, -1.1. And then -0.5, and then we do end up at 1 for cosine of pi over 2, so this is at 1. So here's what occurred. This is going like this. It does go through the origin, and then it hits that. Okay? So I wish I could see that 0 value when that occurred, but it does. It does hit through the origin there. And then we start getting crazy. 2 pi over 3. You know what? Now I'm going to go to pi, which is 4. But you can see these increasing values. I guess I could do 2 pi over 3 is 1, 2.5. Yep, I'm on the over 12. It's so hard with that over 12. Actually, I don't think I like the over 12 in there anymore. I like that it was before, and now I don't. I hate it. All right, hate. 3.1. And then 3.6. I think I went too far. I went to 6 instead of 4. That's why this is so distorted. 5 pi over 6, which is right here, is 3.6. 1, 2, 3.6. I think I went a little too far in that 3.1. That's supposed to be 3.1 right there. And then it's at 4 here. So this continues out. Oh, that's such a bad graph. Okay? All right. And then it's symmetry. On the other side, we have the same thing. And then this loop connects in here. That's what these negative values do, because I am losing time. I'm running out of time. Okay, but here's where the loop came in. Anytime the rectangular graph is below the x-axis, those negative radii values create that loop on the inside of that graph. I don't know what else to call it. And this is called a limacon with a loop. All right. Hey, what's 3 minus 1? Get your calculators out. 2. That's that distance that loop is from the pole. What's 3 plus 1? 4. That's still the farthest value out. And then look at what we have. We have a negative what? A negative what? Cosine. Where is most of the graph at? On the left. There was a negative sign. Most of it would be on the bottom. Positive cosine right. Positive sign up. It'd be the same exact graph. Right? And I can prove that on my Desmos thing as long as we trust AI completely. Right? Isn't that going to be your life? Because it's going to run your life, let's be honest. All right. 2. What did we have here? Sorry, I already forgot what that was. What was our last one? 1. It was 1. 1 minus 3, right? There it is. 3 minus 1. 3 plus 1. See that? And then the thing that I was telling you about, I changed it to plus, and then you got cosine on the right. Same thing. The loops are the same. Change it to sign. It's up, 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 up. Changes to minus, and it's down. These are the conjectures that actually work for just about anything. Right? Gonna get crazy. We've got to do roses next, and that's going to be a little bit different. Okay. All right. Oh man, did I really jack these up? And I could actually, do these on the Desmos. I already did a few though. What time is it? She keeps looking. You're my time lead. Or you look at that clock all the time. What time is it? You knew it. 12:44. She knew it. She knew it. Ay, caramba. Try to draw that one. Let's go. Try to draw that one by hand. 1 and 6. I don't want to. I don't want to. I knew that was coming. I only need a couple points. I'll do the whispering. And then this one. So this is a positive sign. So where can I look at this? It's going to be up. I gotta hit the freeze so the Common Core copying bums don't just copy my screen. Okay, so I still do these. What's sine of 0? 0. 0 plus, that's just 1. That's weird. All right, and then really probably not going to get a lot here. Sine of pi over 2 is 1. 1 times 6. Oh no, I'm off the screen. I hate math. All right, and then what's sine of, I guess I need some more stuff here. Sine of 3 pi over 2. Well, let's do sine of pi. 0. 0 plus 1 is 1. Big difference between these numbers. And then sine of 3 pi over 2 is negative 1. Times 6, negative 6, negative 5. But okay, that's how it works. So I get negative 5. So I go 3 pi over 2 to 5, but then I flip and I go all the way over here. So it's this one. All right. Oh gosh, I guess I should do one more. Like, what's sine of pi over 6? Let's just get a little shape here. Sine of pi over 6, half of 3 is, half of 6 is 3. 3 plus 1 is 4. 1, 2, 3, 4. Okay, that's kind of nice. I guess I have to do a couple negatives there as well. Same thing with this over 6, which is 5 pi over 6. It's over 12 to drive me nuts. Same thing. 1, 2, 3, 4. Okay, so from this, how do I get this? So it does go through the origin. So how do I get my negatives? Let's like kind of hash that out. Well, let's do this one. Let's do 7 pi over 6. Sine of 7 pi over 6 is negative a half. Negative a half of 6 is negative 3. Negative 3 is 2 negative. So it's at 7 pi over 6, comma, 1, 2. That's the loop. So this is going to loop out. So how do I draw this here? So we go like this. Hope I don't embarrass myself here. And then we loop. And then we loop. And then we loop. And then we hit that. Oh, that's god awful. What? What did he say? All right. I made a sad attempt at this loop. Ready, set, go, boink. They would have something close to that. Because what's 6 minus 1? What's 6 minus 1? 5. I know, it's really tough. That's 5 deep there. And then what's 6 plus 1? 7. So that's 7 deep right there. So the loop is inside the other one here. So what I really struggled doing, I should have done this live with you. I started here, and I know I went in this order, and then I just kept going with these points. And then I kept connecting because I knew this is the order that I connected them. And then this is when I went into quadrant 3 and quadrant 4. When I got negative radii values, that's where the loop happened. But really what I did is I did this point, then this point, then this point. Okay, I'll do this anew. I did this point, then this point, then this point, then this point, then this point. And then I started getting into the negative radii values, which reflected. So it is kind of hard to draw this continuously. This is the most challenging one, but at least it gets the idea. I'll tell you what I could do faster on this, and then I'll try to do a better job. Right, left, up, or down. Right, left, up, or down. Where's the majority of it? Left. What's 5 plus 2? 1, 2, 3, 4, 5, 6, 7. What's 5 minus 2? 1, 2, 3. That's where the loop ends. Okay? Now I might do a couple more like, well, it does, cosine of 0 is 1. That's where I get this. This is the very first point. Believe it or not, that's the first point that's graphed. That's 0, comma, negative 3, right? Okay, so that's what we have to kind of understand here. I'm going to go to 5 pi, or pi over 2. Cosine of pi over 2 is 0. That gets me 2. So I at least have these values of 2. 3 pi over 2, same thing. You get 2. All right. And then I guess, let me see. So cosine of pi is negative 1. That's where I get that 7. I guess it is kind of hard to think about this graph without some more points. Yeah. So I'm going to have to think about that some more. So I know it goes through the origin like this, then loops out and gets circular, then loops back to this point, hits the origin, and completes the loop like that. So I guess that's the best way I could do it. I started with my first point, and then know what the loop is supposed to look like, and that's how it's supposed to be. What time is it now? 49. You got beaten over there. Okay, so cardioid, A equals B. Okay, when we have this y equals A plus or minus B, sine or cosine. Let's know our sine cosine rules, up, down, right, left. Cardioid happens when A equals B. A convex, these are all the same. I don't really want to make a big deal about this. This is when A is double or more. Double or more. And then this is what, these are both when A is larger than B. Let's get that straight. Okay. When it's a dimple, A is less than double. I don't like this A over B thing. I've never heard of this before in my life. This seems like just something that somebody made up. Okay. And I never really cared about the difference between convex and dimpled. I just knew the difference ideas going on from there. And then this is when A is less than B as far as a numerical. I should put absolute values around these. I really should. Numerically, this is what we're talking about. Okay, and then ending with this. Input, say it. Okay, so it's y equals blank plus or minus blank and then blank theta. First of all, is this a sine or a cosine? That should be instantaneous. Cosine is a plus or minus? Plus. Okay, so it's a dimpled limacon. What two numbers added together equal 7 and the same two numbers subtracted equal 3? 2 and 5. Which one goes where? Is this the 2 or is this the 5? That's the 2. This is when A is less than B. This is how that occurs. And then you could input, output, and prove these values. They actually do work out. Okay? Cosine of pi is -1. -1 times 5 is -5. -5 plus 2 is -3. All right? So one input, output. This is how simple it is. Okay. Is this a sine or a cosine? Sine. Plus or minus? Minus. See how it works? That's why I love this stuff. And then what plus what equals 4? Then the same two numbers subtracted equals 0. 2 and 2. Remember, these have to be equal. All right, and then what's this one? Sine or cosine? Sine. And then is it plus or minus? Plus. And then what two numbers add to be 5? And then the same two numbers subtract to be 1. 3 and 2. Who goes where? Is this 3 or is this 2? That's 3. That's how you play the game. That's it. Got it? Okay, so that's a good little finish there. We didn't get to that in the last hour, so I guess I did better with you guys. I'm a bum. I didn't grade your test yet. I'm going to go on that right now and not leave today until they're done.